Hi folks, today we're going to talk about ionic bonds. We're very familiar with them in certain substances that we deal with, like here we have salt. So that's something we're very, very familiar with. Now an ionic substance, notice the word ionic, ion. Ionic substances are composed entirely of ions, so that should be easy to remember. If you remember what an ion is, it's something that is positively or negatively charged. Now the simplest form of an ionic substance is a metal and a nonmetal, and that's what we're going to talk about today. We'll make it more complicated later. But bottom line is positives attract negatives, opposites attract. So you have to remember that, and our metals are going to be positive and our nonmetals are going to be negative. Now the metals that we're going to talk about today are our alkali metals and our alkaline earth metals. Those are in the first two columns. We're also going to talk about aluminum. The rest of the metals we're not going to worry about. Now our nonmetals are in blue, We're going to talk about these guys as our nonmetals. But we're not going to talk about the noble gases because the noble gases don't bond with anything. So we're going to ignore them. Okay. So atoms of metals tend to lose their valence electrons. And we saw that in a previous podcast, leaving a complete octet in the next lowest energy level, and that creates an ion. And these things are called cations. You need to write that down. Make sure you get a good definition of cation. They are the metals that are losing their valence electrons. Anions are the opposite. Anions are the nonmetals, and they tend to gain electrons in order to achieve a complete octet, creating an ion. Again, we said some nonmetals because there's some things like the noble gases that do not count. Okay, because the noble gases do not bond. Right? So even though they're nonmetals, they do not bond. These are called anions when they become a negative ion. All right, so why does this happen? Remember the octet rule. Atoms tend to gain, lose, or share electrons in order to obtain a full set of valence electrons. Now, what we're going to talk about today is we're talking about gaining and losing with ionic compounds. Right? What are we gaining and losing? We are gaining and losing the valence electrons, the ones that are in the s and p orbitals, the ones that are in the outermost shell. And the s and p orbitals must be full for the octet rule to work, with the exception of the electron configuration for helium. So if you have something like lithium, which is number 3, lithium is number 3, it will lose one electron to become like helium, which is a noble gas. Right? So it's not going to have 8 electrons, it'll only have 2, but that's okay because you've only got a 1s orbital. Okay. If you have questions about that, come see me in class or go back to the previous podcast from last session. Okay, so we're going to look specifically at sodium and fluorine. Sodium is going to lose an electron, and when it breaks apart and it loses an electron, sodium is left with a positive charge because it has more protons than electrons. Fluorine is going to gain that electron. It's going to suck it in. And when it does that, fluorine is going to gain a negative charge because it has one extra electron compared to what it has for protons. So let's actually look at that. If I have sodium, sodium is number 11 on the periodic table, so it has 11 positive protons in the nucleus. And around it in our first energy level, we have 2 electrons in the 1s level. In our second principal energy level, we have 2 electrons in the s and 6 electrons in the p, for a total of 8 electrons. And in the third energy level, the third principal energy level, which is a whole other shell, right, we have 1 lonely electron. So that's sodium. Let's look at fluorine. Fluorine is number 9 on the periodic table. So it has 9 positive protons in the middle. And again, we have our 1s shell. Down here, my bad. Down here on our 1s shell, we have 2 electrons. And on our second energy level, you'll notice that we have 2 in the 2s and 5 in the 2p. We're 1 short of having a full octet. So we have 1, 2, 3, 4, 5, 6, 7. So we're 1 short. Right? So what's going to happen? Well, sodium, this 1 extra electron that's sitting out there, it's going to come off. And sodium is going to lose that electron, and that electron is going to come over here to fluorine. When it comes over here to fluorine, it's going to join over there. Right? So as a result, sodium is still going to have 11 protons, but it's only going to have 10 electrons left. So it's going to have it's going to have a positive charge because it has 1 extra proton. And that's what this is telling us up here. It's a cation. And fluorine is going to have that extra electron, so it's going to have 10 electrons also. So it is going to have a negative charge. That's down here. Now, we know that opposites attract. So now that the sodium is positive, and the fluorine is negative, the two are going to attract each other. Okay? And that's what ionic bonding is all about. Now, I can draw this a little simpler by simply looking at the valence electrons. Now let's go back and look at sodium. Sodium has one electron in its 3s level in its outer shell. Okay, so if we look at sodium, we can clearly see that one electron in its outer shell, which is right here. We also have 7 electrons in fluorine, and then we're going to add one to it. Okay, so if we do sodium, we would say sodium, and it has 1 electron. And if we take fluorine, fluorine has 1, 2, 3, 4, 5, 6, 7, and you'll notice it's missing one. It doesn't have a pair right here. Right? So what's going to happen is sodium is going to lose its electron. It's going to give it away to fluorine. So now sodium has none. You'll say, well, wait a minute. Sodium is supposed to have 8. Well, let's look back. Sodium does have 8. When you get away with this 3s energy, when you get away with the 3 energy level, right, what's left? Well, the 2 energy level is right under it, and it has a total of 8 electrons. And fluorine also has 8, so everybody's happy. All right, let's do one that's a little bit more complicated. Let's look at calcium and chlorine. Look at your periodic table for calcium, and you'll notice that calcium has 2 electrons in its outer shell. I hate it when the pen does that. 2 electrons in its outer shell. Right? And chlorine has 7 electrons in its outer shell. 1, 2, 3, 4, 5, 6, 7. Well, so what happens? Well, calcium is going to willingly give up its electron, and it's going to give it to chlorine, and chlorine now has 8. So chlorine's very happy, but look at calcium. Calcium's not happy because it still has 1 extra electron over here. So what's going to happen is it's going to find another chlorine atom that has 1, 2, 3, 4, 5, 6, 7 electrons around it, and that electron is going to go up to that chlorine. So calcium will lose its 2 electrons, and they'll go to 2 different chlorines. So calcium will actually bond with 2 chlorines to make that happen. How about aluminum and oxygen? Well, aluminum has 3 electrons. There's aluminum, 1, 2, 3. And oxygen, if we go look at oxygen, again, look at your periodic table, you should be able to find this. Oxygen has 1, 2, 3, 4, 5, 6 electrons. So what's going to happen is oxygen wants to gain 2, and aluminum wants to get rid of 3, so aluminum will get rid of 1 for there, and I'll get rid of 1 for there, and it can't get rid of this one. So it's going to find another oxygen. So it's going to find another oxygen that looks just like the other one. And this oxygen also wants 2 electrons, so aluminum is going to give up 1 to this, and now, oh wait, now this oxygen isn't happy. So now I have to find another aluminum. Yes, this is really what happens, folks. Okay? And it takes 1 of the electrons from aluminum. But now aluminum isn't happy because it still has 2 electrons. Ooh, 2 electrons. That's good. Aluminum has 2 electrons left it is trying to get rid of. Oxygen wants 2 electrons, so aluminum is going to give oxygen those 2 electrons. So there are actually going to be 2 atoms of aluminum bonded to 3 atoms of oxygen. So if you want to look at it, that would be Al2O3. And we'll get into that later. Okay. But just to kind of give you a Lewis dot idea of what happens. All right. When we have charges, we're specifically going to look at, I lost my periodic table. There it is. When we have charges on our periodic table, we specifically are going to look, we already said we're looking at column 1, and we're looking at the alkaline metals, and column 2, the alkaline earth metals, and aluminum. And we're looking at our nonmetals, which exist over here. So how do we know what charges these things take on? Well, here's what I would suggest you do. I would suggest you take a periodic table, just like this one, and I suggest you would take the first 2 columns, and I would like you to fold them. So I would like you to create a fold right there. All right, so if you pause the video, fold the periodic table there. Okay, now the second thing I'd like you to do is fold the periodic table again in such a way that this line moves all the way over here. All right, so that it matches up to that line. So essentially, here's what I've done. I've taken my periodic table, I folded it, and I moved that all the way over so that I cover the D block. So when you're all done, you should only be showing the main block elements, the S and the P blocks, which is what I'm showing here. Right, so hopefully you've been able to do that. And now if you remember when we were looking at these in previous podcasts, we said, well, we have certain numbers of valence electrons, and we said there were 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. If you remember that, you have that from a previous podcast. Now, we also said that the noble gases do not bond because they are very, very happy. They're very content. So they're not going to gain or lose electrons. However, if you look at fluorine, fluorine has 9 electrons, and it would really like to have 10. So what it's going to do is it's going to tend to gain an electron, and when it gains an electron, it has a 1 minus charge. Right? It's going to pick up an electron and get a 1 minus charge. Now, remember, the noble gases don't bond, so we don't care about that. Oxygen is at 8, and if it gains 2 electrons, it can again be just like neon, and it can have 10 electrons around it. Similarly, nitrogen could have 3. Now we could go all the way across here, 4, 5, 6, 7, right? But let's look at sodium for a second. Sodium could gain 7 electrons to become like argon. Okay. Or, wouldn't it be a lot easier for it to lose 1 electron so it could become like neon? And that's exactly what it does. Sodium is going to lose an electron, so it is going to have more protons than electrons, 1 more, so it's going to have a 1 plus charge. Similarly, magnesium would have a 2 plus charge, and similarly, aluminum would have a 3 plus charge, which leaves carbon in the middle, and carbon will actually go either way. It will either add or lose 4 electrons, and it can go either way. So it can go plus or minus 4. All right, so those are charges. You should write them down. Those are the expected charges on the main block elements. Now, you'll notice we're ignoring the D and the F block. That's because their charges are a little goofy, and we're going to talk about them in a future podcast. All right, we have some properties of ionically bonded substances. I'm going to go through these pretty quickly because we're going to see these again in a future podcast. But ionically bonded substances have very high melting points. That indicates that the ionic bond is very, very strong and holds them together really well. For example, you've never seen liquid salt. You've seen salt dissolve in water, but you've never seen it in a liquid form. That's because you've never seen that high temperature. Okay. Salt is very brittle. So if you look at a piece of salt, it's a crystal, and it's a solid. And all ionically bonded substances are solids at room temperature, and they're crystals. And they will be brittle and shatter if you hit them. Most dissolve in water. They break apart into their ions. They're excellent conductors of electricity if they are in liquid state, again, which you've never seen, that's very high temperature, or they're dissolved in water. So they become an excellent conductor if they're dissolved in water, but if they're a solid, they do not conduct electricity at all. So salt does not conduct electricity unless it's dissolved in water. These things look this way. They look like a crystal lattice. So I took this picture at the Smithsonian in Washington a number of years ago. And let's say that the red one is sodium and the blue one is chlorine. You'll notice that sodium essentially surrounds itself on all sides by chlorine. And there's one behind it as well back there. Right? So, and chlorine does the same thing with sodiums on all sides. Right? So essentially what happens is you can't say that this sodium atom gave up its electron to this chlorine. Bottom line is, one of these is very positive, one of these is very negative, and as a result they attract each other. And they form this beautiful little crystal lattice work. So you get cubes, essentially, of salt, and they look like that. And if you look at them under a microscope, you can see that they get these sheer faces on them, and that's because of this crystal lattice work structure that you're seeing with salt. Speaking of salt, let me give you a definition, a chemical definition of a salt. A salt is simply an ionic substance. So when you look it's made out of a metal and a non-metal, so when you look at salt, you think of NaCl. But CaCl2 is also a salt. So MgF2 is also a salt. So when we talk of salt in the vernacular, we mean sodium chloride. When we talk about salt in chemistry, we're not necessarily talking about sodium chloride, so you might need to get that clarified if we ever have a question like that that you are not sure of. Okay? Halides. Halides are simply something that includes a halogen. So for example, all of these above, these are all halides because they're all salts, and they all include chlorine or fluorine or bromine or iodine. right? Whereas something like Na2O is not a halide because it does not include a halogen. Okay, I think we're done. So, in summary, you need to be able to look at an ionic substance. Remember, it's entirely made up of ions. Know that a cation is positive, a metal, and an anion is a non-metal, it's negative. The octet rule determines the charges, and you should be able to do the charges. You should be able to know the 5 ionic properties that I gave you, and you should know the definitions for salts and halides. That's it, folks. If you have questions, ask me in class. I'll see you then. Bye. Have a good day.